Welcome back to Nanoscience and Technology. In this lecture, I'd like to focus on a concept called permittivity as well as conductivity. And that's going to eventually lead us to get to discuss things like quantum dots and what happens in semiconductors and metals, as well as we'll touch on plasmonics and plasmons. All right, so let's start with the easiest topic that I just mentioned, which should be conductivity, something that we are all familiar with. What is conductivity? Well, I hope you could define it yourself in your own words. I like this definition. It's a measure of how easily charge flows. Given a fixed voltage difference. And of course, given the same material and conditions like that. All right, so that's conductivity. It's a measure of how easily charge flows. What about permittivity? I'm sure you've encountered permittivity before, but perhaps you don't have a clear concept on what it is. How would you define it if you had to? Well, this is my definition that's appropriate here. It's a measure not so much of how easily charge flows, but instead of how easily photons propagate in a material. Or another way to think of it is how easily photons flow. Now, it is also a measure, and this is a complementary definition. It's also a measure of how strong an electric field is permitted. Given a fixed voltage difference. All right, and that's where the name comes from, permittivity. It comes from this idea that the permittivity is a measure of how strong an electric field is permitted, or which will result, given a fixed voltage difference. All right. Now, there's several kinds of parameters, or there's several parameters that affect conductivity and permittivity. But the most important one is frequency. So I'd like to divide up our discussion with regard to frequency. All right, so let's start out with the case of zero frequency, or when nothing changes in time. So it's static. All right, so this is the case when the frequency of the electromagnetic field, or the photon, is zero. And in this case, you've probably encountered the basic equations before in perhaps a basic physics class. This is often then a permittivity with the label epsilon, can be described as simply a constant, or a relative permittivity, times the permittivity of free space. And I sure hope you've seen this before. I'll make a note. If not, you can look it up, but this is the relative permittivity, and this is the permittivity of a vacuum or free space. and of course this is 8.854 times 10 to the minus 12 farads per meter. So look that up. You should be already familiar with this. All right, so that's the case when frequency is 0. It's a very simple expression. It's simply a material parameter times a constant, or constant, which is the vacuum constant. All right, what about time varying? So now in time varying permittivity, we have the frequency is not equal to 0. Then we have something called a complex permittivity. Oh, and I forgot to say something up here. This is a real valued permittivity when the frequency doesn't change. Whereas in the time varying case, we have a complex permittivity not only because it's more complicated, but especially because it involves now imaginary numbers. All right, and so the description for this is a function epsilon that now depends on frequency, and it's broken up into two parts, epsilon prime, and tip of the day is to write all this down in your own notes so that you can remember it later for homeworks, for tests, and for projects and topics in the future in your career. So write this down in your notes just like I'm doing. So in this case, we have a function that's a total function that is a combination of two parts. And I hope you can see that the first part is real, epsilon prime, and this is imaginary, this second, epsilon double prime. All right, so this whole term is the imaginary term. And it is, of course, I times a real part. And we're going to talk about this epsilon double prime. Epsilon double prime itself is not in an imaginary number, but of course it's being multiplied by I, the imaginary number square root of minus 1. And this whole term is a function of three parameters. Well, it's also a function of the permittivity of a vacuum. It's a function of the frequency, and it's a function of the conductivity. So let's dive a little bit more into this. And what we need to do is understand all of this so that we can see what happens to materials at different frequencies. It's really important as we consider the wavelength of, or as we consider the effects of nanostructures and for different wavelengths, we need to understand this expression. All right, so let's look at this first term. Well, this is the real part, right? And this is the forward speed, or it's related to the forward speed of the photon or a wave. It is related to capacitance. Or the capacitance of a material. And this is important. If this parameter is greater than 0, we call it a dielectric. Right? It's a dielectric material. It behaves as an insulator. However, if this parameter is less than 0, it behaves as a metal. So this is hugely important. It decides the properties of a material or a surface in a tremendous way. All right, so this is that was the real part. Now this is the imaginary part. And let's see if we can unpack this a little bit. This has to do with absorption, and indeed the energy lost as an EM wave or the collection of photons propagates. Now, in a prior lecture, we talked about absorption at the scale of an atom, and that's all true. Now we're talking about absorption on a macroscopic scale, averaged over a whole bunch of atoms. And so this function describes a kind of approximation of what's really happening to each individual photon. But it's more simple because we don't have to consider each individual photon interacting with any particular atom, but rather we can look at it all as a continuous medium and describe things with continuity. All right, so this is the imaginary part, and it describes the energy lost as the wave propagates, or conversely, the probability of a photon, or of the photon being absorbed. All right, so if you're looking at a problem where you have wave propagation, then you have to consider this. If you have a situation where you're dealing with individual photons, well, this imaginary part then describes a probability of whether to be absorbed or not. Okay, so let's talk about metals and what it means to behave as a metal. All right, so what's going on with a metal? And this is the key that I hope you remember from the distinction in the past and earlier in this course, as well as in your prerequisites, that metals have a free electron sea, or a sea of free electrons. You know, the electrons that are not connected directly to any particular atom, these electrons act as a kind of sea of electrons, or sometimes in some literature it's called an electron gas, or a gas of electrons. And that's really the picture you should be thinking of, that the electrons are floating around as a kind of gas within the solid, and they are able to flow freely. All right, and so in this case, then, we can identify what this function is, and your book has this written down in it as well, but it's missing a term. It should have this very first term, where the permittivity of a vacuum needs to multiply this quantity that is already written in your textbook. It's this constant that's missing from your textbook, and it should be added. All right, so then for metals, this real part is a fairly simple function of frequency. And I'll explain these parameters in just a moment. All right, so when we have a sea of free electrons, then the real part of the permittivity can be written in this function, and you can see it's clearly varying with frequency. And then the imaginary part can be written like this, and also note that this term here is missing from your textbook equation. It should be added. Okay, so now we have a way to describe the permittivity, the complex permittivity, both the real and imaginary part, if we know that the material is a metal. And so what are the key parameters that I've written down here? Well, let's take a look. I've got a parameter, of course, the permittivity of a vacuum. We already know what that is. Then we have this parameter here, which is the plasmon frequency, or the plasma frequency, and then we have a constant gamma. All right, so if we can describe and define what those just two parameters are, then we're going to know how to describe the permittivity of any given material. So let's write down what those are. All right, now of course F is the photon frequency. Right, and so for example, green light that we can see is green has a frequency of around 540 terahertz. All right, so a couple hundred terahertz would be visible light. All right, and then this parameter gamma is a damping frequency. and it's a kind of coefficient. And then this F sub p is the plasma oscillation frequency. And there's a simple expression to figure out what that is, fairly simple. And it's proportional in a metal to the density of electrons, n sub e, the charge of an electron squared, divided by the mass, or the effective mass of an electron, and then again the permittivity of a vacuum. All right, so let's see, Ne, let's write down what these are. And then we know what the rest of these are. Okay, so if we control the doping, the number of charges that are in a given material, for example in a highly doped semiconductor, then we can control what this oscillation frequency is. Or perhaps it naturally occurs in the material. All right, now this description is good for most metals. For example, aluminum. And let's put in some numbers. So the plasma frequency for aluminum is about 3,600 terahertz. Right? And that happens to be in the UV, or the ultraviolet, actually quite far in the ultraviolet. So we can't see that, but that would certainly burn our skin and give us sunburn. And also, we can see that gold and copper, which are different than some metals because they appear to us as being somewhat yellow, they have a plasma frequency in the visible. And what that means is that so red is reflected more, and reflected more in particular than blue colors. And since the effect is slight, it doesn't look red, but rather looks somewhat yellow. Okay, so we've got is that for frequencies less than the plasma frequency, this leads to higher reflection. Since the plasma is faster. But for frequencies that are greater than the plasma frequency, this is higher transmittance. This leads to a higher transmittance of the material for that frequency, since the plasma is slower, and you might think of it that it cannot keep up. All right, so keep in mind here what we're talking about is a gas, an electron gas that's charged, and then we have a photon coming in, or an electromagnetic wave that is oscillating and resonating with that gas. And what we're saying by this description is that there's a resonant frequency where the interaction is greatest, but when the frequency is less than the plasma frequency, then the gas can oscillate with the incident electromagnetic wave, and that ultimately leads to a reflection. Whereas if the frequency of the incoming photon or wave is faster than the plasma frequency, generally then the wave passes through the material with more transmittance because it can't keep up. Now, so far we've talked a lot about the permittivity, and we've used equations to talk about it, but I'd like to talk about it now with respect to a graph, and I'd like to give you a sense, an intuitive sense of what's going on the scale of the molecule, so that you can see how this affects photons as they interact with the material. So this is a plot from Wikipedia that shows the real and the imaginary parts of the permittivity, and it's on a scale that is with frequency, but notice that it's in a logarithmic format. And the thing to see here is that we've got microwave frequencies here, infrared, then visible around here in terahertz, and then UV and many hundreds of terahertz up here. All right, now we can see that the real part of the permittivity for low frequencies generally tends to be flat. And then what's illustrated here is that it changes, and then it has a kind of oscillation here. It goes up and then down and then steadies out, and then goes up and then down and steadies out. Now this is very, very common, and what's happening here is that for low frequencies there is a change in a molecule or in a material which can be characterized as an ionic change, and in the very low frequencies. And then secondly, there are changes in a molecule or in a material that could be considered dipolar, and both of these have to do with a kind of resonance of the charge within the material itself. And we're not going to get into the great details there, but these are basically two types of oscillations of the local charge within the material. Now, for higher frequencies, there are resonances or oscillations that are between atoms. And in this case, we can wind up having atomic oscillations between atoms, perhaps within a molecule or perhaps within the solid itself. And then at even higher frequencies, there can be oscillations that are called electronic, but basically these are the oscillations of an electron within an atom. And sometimes those oscillations have to do with an electron receiving energy and going to a higher orbital state and then coming back down, or perhaps some other more complex processes. But the basic point here is that there are different kinds of reactions that a material or a molecule can have to an incident photon. And which one of those is going to be selected depends largely on frequency. All right, one other thing to show you here, just to expose you to this, and that is that, that there are different ways that we can show this very same set of parameters, the real part of the permittivity and the imaginary part of the permittivity. This graph on the left is very similar to what we saw on the prior slide, where we have the value, in this case normalized by the vacuum permittivity, and then mapped versus frequency. Now, the very same data is shown in this second graph on a logarithm scale, where we use the units of wave number, which is simply another way to express the frequency or the wavelength, and you can see the conversion right here. And so what we can see here is at this particular wave number, there is a very sharp dip in the real part. And notice that this happens at a frequency that is the plasma frequency. And that's very, very typical. And in this plot, the plasma frequency shows up right here, whereas in the other plot, which is of the same data, it occurs right here. And notice that then this plasma frequency occurs when the real part of the permittivity crosses the zero. Okay? And so I'm not going to unpack all of this, but I just wanted you to get the sense that the real part has a zero crossing of the plasma frequency, and ultimately these are some of the trends, and there's different ways to graph this.